Welcome to this walkthrough of problem number 85, Maximal Rectangle. In this session, we'll explore how to approach this challenging problem, breaking it down step by step to understand the key concepts and algorithms that will help us solve it efficiently. Let's dive in. The problem we're working on is called Maximal Rectangle. The goal is to determine the area of the largest rectangle that can be formed within a given binary matrix, where the rectangle consists entirely of one S. The input is a 2D list of characters, where each character is either 0 or 1. The output is an integer that represents the area of this largest rectangle. For example, consider a matrix where each row contains a mix of 1s and 0s. Within this matrix, you need to identify the largest possible rectangle filled entirely with 1s and calculate its area. This is the problem we aim to solve. Now, let's look at an example. If the input matrix is shown as a grid of rows and columns, the largest rectangle of 1s spans certain rows and columns, and its area is calculated as 6. Specifically, this rectangle is formed by the second and third rows, extending across columns 3 to 5. In contrast, if the matrix is empty, meaning there are no rows or columns, the output will simply be 0 because there are no rectangles to form. These examples highlight the variety of scenarios we might encounter. In another example, consider a matrix with just one element, which is 0. In this case, there's no possibility of forming any rectangle of 1s, so the area is also 0. However, if the matrix contains a single element that is 1, then the rectangle is just that one element itself, and its area is 1. These cases demonstrate how the input size and values directly influence the outcome. Additionally, for the single element matrix containing only 1, the maximal rectangle is simply the element itself, and its area is determined to be 1. These examples make it clear how the problem scales from small inputs, like a single element, to larger, more complex matrices. Understanding these scenarios prepares us to handle edge cases and more intricate configurations of the matrix efficiently. Finally, let's review the constraints and edge cases for this problem. The matrix can have up to 200 rows and 200 columns, and each element will always be either 0 or 1. For edge cases, if the matrix is empty, the area is 0. If it contains only one element, the output depends on whether the element is a 1 or a 0. For matrices filled entirely with 0s, there are no rectangles of 1s, so the output is 0. Conversely, if the matrix is filled entirely with 1s, the maximal rectangle will cover the entire matrix, and the area will be the total number of rows multiplied by the total number of columns. These constraints and edge cases provide a clear framework for solving the problem effectively. To begin solving the maximal rectangle problem, one intuitive approach is the brute force method. Here, we systematically explore every possible rectangle within the binary matrix. For each rectangle, we check if it is completely filled with ones and calculate its area. While this approach ensures all possibilities are considered, it requires identifying all combinations of top left and bottom right corners for rectangles. The downside is its time complexity, which grows cubically with the number of rows and columns in the matrix, making it infeasible for larger inputs. Despite its simplicity and minimal space requirements, this method is computationally expensive and impractical for real-world scenarios involving large matrices. A more efficient approach utilizes histograms to simplify the problem. The key insight is to interpret each row of the matrix as the base of a histogram, where each column represents the height of consecutive ones above it, including the current row. To determine the largest rectangle in such a histogram, we use a monotonic stack, a powerful tool for efficiently calculating areas. The process involves building a height array for each row, where each element corresponds to the height of the histogram at that column. As we traverse the matrix row by row, this height array is updated dynamically. Then, leveraging the stack, we compute the largest rectangle for the current histogram and keep track of the maximum area found. This method processes the matrix in linear time per row, resulting in a total time complexity of O(n*(m), which is a significant improvement over brute force. While it requires additional space for the height array and the stack, the efficiency gains make it a practical solution for larger matrices. The chosen strategy for solving this problem is the optimized approach using histograms. Its strength lies in reducing the 2D problem into a series of 1D problems, which can each be solved efficiently. The key observations driving this approach include recognizing that consecutive ones in a column form histogram heights and that the largest rectangle in such a histogram can be computed with a stack. By iterating row by row, the height array is updated dynamically, allowing us to solve the problem in linear time for each row. This makes the overall time complexity O(n*(m), which is optimal for this problem. The ability to scale well with larger matrices and the realization that a 2D rectangle problem could be transformed into a 1D histogram problem were pivotal breakthroughs, cementing this approach as the most practical choice. While this approach is highly efficient, it does come with minor trade-offs, such as the additional space required for the height array and the stack. However, the performance benefits far outweigh these costs. By reducing the problem to a series of histogram evaluations and using a stack-based algorithm, we achieve a solution that is both scalable and computationally efficient. In contrast, the brute force approach, though straightforward, is not practical due to its high time complexity. Ultimately, the histogram-based method stands out as the ideal solution for the maximal rectangle problem, balancing efficiency and scalability to handle even large matrices effectively. To solve the maximal rectangle problem, we begin by understanding the input and the brute force approach. The input is a binary matrix of size m by n, where each cell contains either 0 or 1. The goal is to find the largest possible rectangle that is completely filled with ones and return its area. A straightforward brute force approach involves iterating through all possible rectangles in the matrix. For each rectangle, we check if it is entirely filled with ones and calculate its area if valid. Then, we keep track of the maximum area found so far. To implement this, we start by iterating over all potential top left corners of the rectangle. This is done using two nested loops, one iterates through the rows and the other through the columns, treating each cell as the starting point of a potential rectangle. Once a top left corner is identified, the next step is to expand the rectangle by selecting all possible bottom right corners. Two additional nested loops are used here, one to iterate through rows starting from the top left row and another to iterate through columns starting from the top left column. This process generates all possible rectangles that can originate from the selected top left corner. For each rectangle, we need to validate whether it is entirely filled with ones. To do this, we again use nested loops to traverse all the cells within the rectangle boundaries. If any cell contains a 0, the rectangle is marked as invalid, and we skip further checks for that rectangle. If the rectangle is valid, we calculate its area using the formula, area equals the number of rows times the number of columns. This area is then compared to the current maximum area, and we update the maximum if the new area is larger. After iterating through all possible rectangles, the final step is to return the value of max_area, which stores the largest rectangle area filled entirely with ones. While this brute force approach guarantees correctness, it is computationally expensive due to its high time complexity. For each rectangle, we iteratively validate that all cells within its boundaries contain ones. This contributes significantly to the overall complexity, which can be broken down as follows: selecting the top left corner takes O(m*(n), selecting the bottom right corner takes another O(m*(n), and validating the rectangle takes O(m*(n) in the worst case. This results in a total time complexity of O(m times n cubed, making this approach impractical for larger matrices. It highlights the necessity of optimizing this process for better performance. To better understand the mechanics of the algorithm, let's review the key data structures and variables used. The binary matrix itself serves as the input, with constant time access to individual cells, which is crucial for efficient checks. The variable max_area is initialized to 0 and keeps track of the largest area found during the execution. Temporary variables such as I, j, k, and l are used to define the boundaries of the rectangles during iteration. These variables allow us to dynamically define the top left and bottom right corners of each rectangle, enabling systematic exploration of all possible configurations. To visualize the data flow, consider the outer loop, which selects a specific cell as the top left corner. For example, in a 4x4 matrix, choosing I equals 1 and j equals 2 selects the cell in the second row and third column. From this starting point, the rectangle is expanded step by step by adjusting the bottom right corner. For instance, the rectangle might grow to include cells from row 2 to row 3 and column 3 to column 4. Once the rectangle's boundaries are defined, every cell within those boundaries is checked to ensure all are ones. If the validation passes, the rectangle's area is calculated and compared with max_area. If the new area is larger, max_area is updated accordingly. Finally, there are some key optimizations that can significantly improve the algorithm's efficiency. One simple optimization is early termination during validation. If a 0 is encountered while checking the cells of a rectangle, we can immediately stop further validation for that rectangle, saving unnecessary computation. A more advanced optimization involves using pre-processing techniques, such as dynamic programming or histogram-based methods, to reduce the time complexity from O, open parenthesis m times n close parenthesis cubed, to a much more manageable level. While these advanced methods are beyond the scope of this discussion, they are worth exploring for solving this problem on larger matrices effectively. Here, we're implementing the maximal rectangle function in Python. First, we handle edge cases by checking if the matrix is empty or if its first row is empty, and we return 0 in such cases. Next, we calculate the number of rows and columns in the matrix and initialize an array called heights to store the heights of histogram bars for each column. We also initialize max_area to keep track of the largest rectangle area found so far. Then, for each row in the matrix, we update the heights array. If the current cell in the matrix contains a 1, we add 1 to the corresponding column and heights, otherwise, we reset that column to 0. After updating the histogram heights for the current row, we calculate the maximum rectangle area for this histogram using a helper function called largest rectangle area. Finally, we update the max_area variable with the maximum value found so far and return it at the end. In the largest rectangle area helper function, we calculate the largest rectangle area for a given histogram. We start by appending a 0 to the heights array to ensure we process any remaining bars in the stack at the end. We then use a stack to track the indices of histogram bars, and a variable max_area to store the maximum area encountered. For each height in the heights array, we check if the current height is less than the height of the bar at the index stored at the top of the stack. If it is, we pop the top of the stack to calculate a rectangle's area using the popped height as the smallest bar. The width of the rectangle is determined by the difference between the current index and the index at the new top of the stack, or the entire width if the stack is empty. We then update max_area accordingly. After processing all heights, we remove the appended 0 from heights and return the maximum area found. Here, we start by defining a class named solution with a method maximal rectangle that takes a 2D character array matrix as input. This matrix represents a grid of 1s and 0s. If the matrix is null or empty, we immediately return 0, as there's no rectangle to calculate. Next, we determine the number of rows and columns in the matrix and initialize an integer array heights to store the heights of histogram bars for each column. We also declare a variable max area to keep track of the largest rectangle area found so far. Then, we iterate through each row in the matrix. For each column in the row, we update the heights array. If the current cell is 1, we increment the height for that column, otherwise, we reset it to 0. This transforms the matrix row into a histogram representation. After updating the heights for a row, we calculate the maximal rectangle area for the current histogram using a helper function largest rectangle area, updating the max area variable accordingly. Finally, after processing all rows, we return max area as the result. The helper method largest rectangle area is responsible for finding the largest rectangle area in a histogram represented by the heights array. To make calculations easier, we extend the heights array by adding a 0 at the end, ensuring that all bars are eventually processed. We use a stack to keep track of indices of histogram bars in increasing order of their height. As we iterate through the extended heights, we check if the current bar height is less than the height of the bar at the index stored on top of the stack. If it is, we pop the stack, calculate the rectangle area using the popped height as the smallest bar, and update max area if the new area is larger. The width of the rectangle is determined by the difference between the current index and the index on the new top of the stack, or I if the stack is empty. Finally, we push the current index onto the stack. This ensures that all bars are processed efficiently, and once the loop is complete, max area contains the largest rectangle area for the histogram. To solve the maximal rectangle problem, let's work through a simple example step by step. The given matrix has 4 rows and 5 columns. To start, we initialize some variables. Rows and cols store the dimensions of the matrix. Heights is an array of zeros with a length equal to the number of columns, and max_area is set to 0 to keep track of the largest rectangle area we've found so far. For row 0, we update the heights array based on the values in the row. A 1 increases the corresponding height, while a 0 resets it to 0. This gives us heights equals 1, 0, 1, 0, 0. Next, we pass this heights array to the largest rectangle area function. Before processing, we append a 0 to the end of the heights array to handle any remaining indices, resulting in 1, 0, 1, 0, 0, 0. Now, we process the histogram represented by the heights array. Starting from left to right, we push indices onto a stack when the current height is greater than the height at the top of the stack. For this row, we push index 0 since the height is 1. When we encounter a smaller height, we pop the stack, calculate the area of the rectangle formed, and update the maximum area if necessary. Here, we calculate an area of 1 using height 1 and width 1. Then, we continue pushing the remaining indices. At the end of this step, the maximum rectangle area for this row is 1, so we update max_area to 1. Moving on to row 1, we update the heights array to 2, 0, 2, 1, 1, based on the matrix values. Again, we call largest rectangle area, appending a 0 to the array for processing, resulting in 2, 0, 2, 1, 1, 0. Processing this histogram involves similar steps. Here, we calculate an area of 2 using height 2 and width 1. Once finished, the maximum rectangle area becomes 2, and we update max_area accordingly. For row 2, the heights array becomes 3, 1, 3, 2, 2 after updating. When we process this histogram, we find a maximum rectangle area of 6, which involves using height 2 and width 3 to calculate the area. This updates max_area to 6. Finally, for row 3, the updated heights array is 4, 0, 0, 3, 0. Processing this histogram does not yield a larger rectangle area than 6, so our max_area remains the same. With all rows processed, the final output for this example is max_area equals 6. Now, consider another case where the entire matrix contains only zeros. Here, the heights array remains 0, 0 for all rows, and the largest rectangle area function consistently returns 0 since no rectangles can be formed. As a result, the final output for this case is max_area equals 0. For a single row example, we have a matrix with one row containing 1, 1, 1, 0, 1. Updating the heights array gives 1, 1, 1, 0, 1. Passing this array to the largest rectangle area function, we process the histogram by pushing indices for heights greater than those at the top of the stack. As we pop indices, we calculate areas of 1, 2, and 3, using the respective heights and widths. The largest rectangle area for this row is 3, so the final output is max_area equals 3. This demonstrates how the algorithm handles a matrix with just one row effectively. To analyze the time complexity, we start with the outer loop, which traverses through each row in the matrix. If the matrix has m rows and n columns, this traversal will take m time since we are iterating over all the rows. Within each row, there is an inner loop where we update the heights array. This involves processing all the columns, taking n time for a single row. When we consider all rows, this step contributes a total of m*n complexity. After updating the heights array for a row, we calculate the largest rectangle in the histogram using the largest rectangle area function. This function uses a stack-based approach to process the heights array in n time for each row. Since it is called for all m rows, the total cost for this step is also m*n. Now, combining the time complexities of the histogram construction and the area calculation, we get a total time complexity of m*n plus m*n, which simplifies to m*n. Shifting focus to space complexity, the main structure we use is the heights array, which stores the histogram heights for each column in a row. Its size is equal to the number of columns, so it requires n space. Additionally, the largest rectangle area function uses a stack to store indices of histogram bars during its computation. In the worst case, all columns in a row could be pushed onto the stack, resulting in another O(n) space usage. Since no other major data structures are used, the auxiliary space requirements are minimal. Combining the space for the heights array in the stack, the total space complexity becomes O(n) plus O(n), which simplifies to O(n). Let's now look at different scenarios. In the best case, where the matrix only contains zeros, the heights array remains 0 across all iterations, and the stack operations are minimal. This results in a time complexity of O(m*(n). In the average case, where the matrix is a mix of ones and zeros, the time complexity also remains O(m*(n), as each row and column is still processed. For the worst case, where the matrix is filled entirely with ones, the heights array grows continuously, and the stack operations are maximized. Even in this case, the time complexity does not exceed O(m*(n). When comparing this approach to the brute force method, we see a significant improvement. A naive approach would involve examining all possible rectangles in the matrix by iterating over all pairs of rows and columns, validating each rectangle, and calculating its area. This would require nested loops over all possible row and column pairs, leading to a time complexity of O(m²*n². In contrast, the optimized approach leverages the histogram-based calculation and a stack to efficiently compute the maximal rectangle area. By reducing the time complexity to O(m*(n), it becomes practical to handle much larger matrices while ensuring accuracy and efficiency. To solidify the time complexity analysis, we can break it down mathematically. Updating the heights array requires O(m*(n) operations since each cell in the matrix is processed exactly once. The stack operations in the largest rectangle area function are proportional to the number of columns, O(n), and this is performed for each of the m rows, resulting in another O(m*(n) contribution. These two steps dominate the algorithm's runtime, confirming that the overall time complexity is O(m*(n), which is optimal for this problem. On the space complexity side, the algorithm uses O(n) space for the heights array and the stack combined, making it both time efficient and memory efficient for practical applications. When solving maximal rectangle problems, there are several common mistakes to watch out for. One major issue is not pre-computing data for optimization. For instance, calculating the sum of every possible rectangle directly can lead to excessive redundant computations and cause time limit exceeded errors on large inputs. Instead, techniques like prefix sums or dynamic programming are essential for efficient solutions. Another frequent mistake involves incorrect submatrix boundaries. Off by one errors in indexing can result in inaccurate area calculations or even out-of-bounds errors. It's also important to account for matrices of any dimensions. Assuming the matrix is always square, rather than handling both mxn and nxn shapes, can lead to logic failures. Edge cases are another critical area where errors occur. Forgetting to handle scenarios like empty matrices filled with only zeros, or very small inputs, such as 1x1 matrices, can cause runtime issues or yield incorrect results. Finally, avoid relying on inefficient brute force methods for large inputs. Matrices of size 10,000 or more require optimized approaches, as brute force will almost always exceed time limits. Now, let's touch on some key insights to keep in mind during interviews. Recognizing patterns is a crucial skill for matrix-based problems. For example, problems that focus on finding the largest rectangle or square often leverage solutions built from smaller subproblems or apply histogram-like reductions. It's vital to practice identifying these recurring patterns. Dynamic programming is another central concept. Interviewers typically expect you to use it to optimize the solution and reduce time complexity, so be prepared to explain your state transitions and why they work. Edge cases are frequently tested as well. Make sure your solution accounts for scenarios like matrices filled entirely with zeros or ones, large inputs, and irregular dimensions. Lastly, when proposing multiple approaches, always explain their trade-offs, such as comparing space and time complexity. This demonstrates to the interviewer that you have a deeper understanding of the problem space and can evaluate the efficiency of different strategies. There are several related problems that can help reinforce your understanding of maximal rectangle concepts. Problem 84, largest rectangle in histogram, is foundational for understanding how to optimize rectangle-related problems using stacks. Problem 221, Maximal Square, is closely related but focuses specifically on squares instead of arbitrary rectangles, using dynamic programming to solve. Of course, Problem 85, Maximal Rectangle, is the direct problem we're discussing and combines techniques from both dynamic programming and histogram logic. Lastly, Problem 304, Range Sum Query 2D, Immutable, emphasizes the importance of pre-computing sums for optimization. While it addresses a slightly different problem space, the techniques involved can significantly improve your ability to handle matrix-based optimizations in general. Finally, let's explore some alternative approaches and their trade-offs. The brute force method, while straightforward and simple to implement, has a time complexity of n cubed * m cubed for a matrix of size m by n, making it impractical for anything but the smallest matrices. Dynamic programming is a more efficient alternative. By storing intermediate results, such as the largest rectangle ending at each cell, you can reduce the time complexity to m * n. Another approach is stack-based histogram reduction, which involves converting each row of the matrix into a histogram representation and applying the largest rectangle in histogram solution. Though optimal for certain variations, it requires careful attention to detail during implementation. Lastly, prefix sums can be a powerful tool for quickly calculating the sum of any submatrix. While this doesn't directly solve the maximal rectangle problem, it's particularly useful for simplifying range queries and can be adapted to certain problem variations. Great job making it to the end. We've summarized the key points of the maximal rectangle problem, highlighting the importance of efficient algorithms and stack-based methods. Thanks for watching, and we hope this session inspired you to tackle similar problems with confidence. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!